You know that feeling when you're staring at a puzzle and you just know it's impossible? But how do you actually prove there's no solution? Now, what if that puzzle had, say, millions of variables? Well, today we're going to look at this really cool idea called the replacement framework. It's a whole new way of thinking that boils down the very nature of logical proof to one single beautiful rule. All right, so here's our game plan. First, we'll tackle what a proof even is. Then, we'll dive into what I'm calling a logical Tower of Babel, all these clashing systems. After that, we hit the jackpot, the one golden rule that ties them all together. We'll see how it unifies everything, and then wrap up with why this is a huge deal for the future. Okay, first up, the puzzle of proofs. Seriously, how do we prove something is logically impossible? This isn't just an abstract thought experiment. It's at the heart of everything from pure mathematics to making sure the software on your phone isn't broken. You know, we actually do this all the time without even thinking about it. When you're doing a Sudoku puzzle, what are you doing? You're looking for contradictions. You pencil in a 5 and then realize that forces another 5 into the same row. Bam, contradiction. You've just proven your first idea was wrong. That's a proof, just a tiny one. Right, but how does that scale up? I mean, it's one thing for a little 9 by 9 grid. It's another thing entirely for a computer trying to prove that a super complex formula with literally millions of variables has no solution at all. How can a machine prove a negative and be 100% sure about it? Which brings us to section 2, a logical Tower of Babel. Because for a very long time, the answer to that question has been, well, really, really messy. And that's the exact problem the replacement framework sets out to fix. See, for decades, the world of proof complexity was kind of like that Tower of Babel. You had all these brilliant researchers building different proof systems. Think of them as unique toolkits, each with its own special language and rules, all designed to find contradictions. The thing is, they all worked, but none of them spoke the same language. And this really shows you what I mean. On one side, you've got something called the resolution system. It's all about smashing logical statements together and canceling things out. But then, on the other side, you have the cutting plane system, which treats the whole thing like a geometry problem. It literally carves away pieces of the solution space. They're both trying to do the same thing, but they look like they come from completely different planets. Which leads us to the big idea, the one golden rule. Finding that beautiful simplicity in all this complexity. So the question is there some single simple idea that connects all these different approaches? And the answer, amazingly, is yes. Okay, so to get there, we need to agree on a basic building block. In logic, we call this a clause. Just think of it as one rule in the puzzle, something like A or B or not C. The whole puzzle is just a big collection of these clauses, and they all have to be true at the same time for the whole thing to work. Now here's the really clever part. Every single one of those clauses has a unique weakness, a kryptonite. It's the one and only combination of true and false that makes that specific clause false. So for our A or B or not C example, its kryptonite is when A is false, B is false, and C is true. That specific combo is what we call its zeroing assignment. And this one single idea, that every clause has a personal kryptonite, that is the key that unlocks everything. This is the golden rule of replaceability. Okay, so what is this rule? It's called replaceability, and it's brilliant. It says you can add a new clause, a new fact, to your proof if and only if its kryptonite, that one thing that makes it false, totally breaks what you already know is true. Let me say that again. A new idea is valid if assuming it's false causes a complete contradiction. That's the whole thing.
And this gives us a really clear step-by-step test. Step 1, you propose a new clause you think might be true. Step 2, you find its unique kryptonite. Step 3, you apply that false scenario to all your existing facts. Step 4, you see if everything blows up, if you get a domino effect of contradictions. And if it does, step 5, your new clause is valid. You can add it to the proof.
All right, on to part 4, unifying the systems. So, we've got this one simple rule. How in the world does that bring order to that whole logical Tower of Babel we were talking about before? Well, here's the big reveal. It turns out that all those different proof systems, all of them, were secretly using this exact same rule the whole time. They just didn't know it. Their different rules and languages were just different costumes for the same fundamental underlying truth. And this is the aha moment, straight from the source. For any of those old systems to be considered sound, which just means they don't prove false things, they have to follow a specific logical property. And guess what? That property is the definition of replaceability. So the entire time, every single valid proof they ever created was already a replacement proof. They just didn't have a name for it. So this means the replacement framework has this trifecta of awesome properties. It's sound, which means it's never wrong. It's complete, which means if a proof exists, it can find it. And, the big one, it's universal. It's not just another system, it's the master key that shows how all the other systems are related. So, moving on to Section 5, from idea to action. This is all great as a theory, right? It's a really nice, clean idea. But can you actually do anything with it? Is it operational? Absolutely. This is where the framework gets really practical. It shows how that abstract golden rule we talked about leads directly to a concrete operation. And get this, the simplest, most basic way to actually do a replacement turns out to be that resolution rule we mentioned earlier. So resolution isn't just some random system, it's the fundamental building block of logical deduction. And this next part is just mind-bending. The framework proves that for any given problem, it doesn't matter what path you take. No matter what valid replacement steps you make or what order you do them in, you will always arrive at the exact same final set of facts. It's called the halting set, and it's like a predictable final destination for any proof. Okay, last section, the future of proof. So we have this elegant, universal theory that says every proof has a single predictable endpoint. Why does this matter? What does this change? Well, a whole lot, actually. By getting us to focus on the core meaning of a problem, the semantic essence, instead of just the quirky rules of one system, it opens up all kinds of new research directions. We're talking smarter SAT solvers, way more powerful tools for automated reasoning, and maybe, just maybe, a real understanding of what makes some problems so incredibly hard to solve. Really, the key takeaway here is bigger than just computer science. It's a lesson about how to solve hard problems in general. If we want to make big leaps forward, we have to stop getting obsessed with the surface-level details that make different approaches look different and start looking for the fundamental truths that actually unite them. And that really leaves us with a final, big question to chew on. This framework found a simple, unifying idea hidden under decades of complicated stuff. So you have to ask, what other breakthroughs are just waiting out there in fields like biology or economics or anything else for someone to find that simple, unifying principle that's been hiding in plain sight all along?